For half the year, parts of India are submerged under violent torrential rains. Months later, that same soil is baked into cracked, bone-dry earth. How can one country experience such binary extremes? In Tamil, we might ask, Odu natil epari ipari patta idu veru tarvangale tana mudiyam. The source of these conditions actually lies about 14 kilometers directly above our heads. Right at the Earth's equator, intense, direct sunlight constantly heats the surface. This causes the air to warm up rapidly, expand, and rise all the way to the upper limit of the troposphere. This mechanism is the Intertropical Convergence Zone, or ITCZ. Because of the intense heat and rising air, it creates a massive band of low atmospheric pressure, often referred to as the thermal equator. Winds from the tropics converge into this low-pressure area from both hemispheres. As this warm, moist air meets, it is forced upward, where it cools and expands to form massive cumulonimbus clouds and heavy thunderstorms. Because of this immense upward pull of moisture, wherever this band of low pressure sits on the Earth, extreme and continuous rainfall inevitably follows. But because the Earth tilts on its axis, the area receiving the most direct sunlight shifts throughout the year. As the heat moves, the ITCZ must migrate along with it. By July, this low-pressure band moves significantly north, forming the Northern Intertropical Convergence Zone, or NITCZ. By January, the sun moves south, and the ITCZ retreats toward Australia, creating a southern rain band and leaving the north behind. This is a planetary-sized pendulum. Every 6 months, this enormous atmospheric engine swings back and forth, dragging the world's primary rain belts across the globe. Tracking the position of this invisible, shifting line explains why the Indian subcontinent experiences such violent seasonal swings. To see how this affects India, we have to look specifically at the subcontinent's borders during the peak of July. During this month, the ITCZ parks itself directly over the Indo-Gangetic Plain. This creates an intense low-pressure zone that acts like a massive atmospheric vacuum. It forcefully pulls in moisture-laden winds from the Indian Ocean and sweeps them across the land. This is the Indian summer monsoon, then Merku Paruvamaje. It is the localized result of a massive global migration. The survival of India's agriculture and its water resources is entirely dependent on this global low-pressure band arriving exactly on schedule. By January, the timeline has shifted. The rain-bringing ITCZ has completely retreated far south of the equator. As the low pressure leaves, it is replaced by the subtropical high-pressure belt. The warm air that rose at the equator has now lost its moisture. High in the atmosphere, it cools down and physically sinks back to Earth around 30 degrees north. This heavy, sinking air creates high-pressure conditions. Because the air is pushing down, it physically prevents clouds from forming, ensuring total dryness across the region. This pressure forces the surface winds to reverse completely. Now, instead of drawing moisture in, dry air from the landmass is pushed outward toward the sea. This invisible, crushing weight of sinking dry air is what guarantees India its settled, rain-free winter months. Even though India spends its winter under a cold, high-pressure belt next to the freezing expanse of Central Asia, the country itself does not freeze solid. The country is uniquely protected by the Himalayas, Imayamalai, rising as a massive, unbreakable wall across the northern border. These mountains are high enough to interact with high-altitude winds. They physically split the subtropical jet stream, forcing the main branch to curve south around the range. While the high-pressure system above keeps the skies dry, the sheer height of the mountains blocks the lethal, freezing surface winds blowing out of Central Asia, leaving the Indian plains untouched. The shifting ITCZ delivers vital water, the sinking air clears winter skies, and the Himalayas preserve the warmth. Together, these forces create the specific conditions that define the Indian climate.